In this video, we are going to look at special triangles and use them to find exact ratios for angles that have a reference angle of 35, 45, or 60 degrees without using a calculator. There are two special triangles that you are expected to remember. I'm going to develop them with you to hopefully help you remember them better. So for the first special triangle, we draw a right angled triangle that is isosceles. So if you remember, isosceles means it has two lengths that are the same. And we are going to say that those two lengths are length 1. Not only does an isosceles triangle mean that these two lengths are the same, it also means that these two angles are the same. So we know that one of our angles is 90 degrees, so we are left with 90 degrees. So 90 degrees divided by 2 is 45. So each of these angles are 45 degrees. And then because this is a right angle triangle, we can use Pythagorean theorem to find the length of that hypotenuse. So we know c squared, the longest length, is equal to a squared, which is 1 squared, plus b squared, which is 1 squared. 1 squared is 1, so 1 plus 1, so c squared is equal to 2, and then when you take the square root of both sides, you get the square root of 2. So the hypotenuse of this triangle is root 2. So this is the first triangle that you need to remember. It's an isosceles triangle with two 45-degree angles. You have length 1, and then the hypotenuse, which is the longest length, is root 2. The second triangle, we actually start off with an equilateral triangle. So an equilateral means all of the lengths are the same, and we're going to say that all lengths are length 2. We could do length 1, but then when we cut it in half, we're ending up with a fraction. Either way it would work because you're always talking about ratios, but length 2 is easier because we can divide by 2 nicer. So you have 2 by 2 by 2. And also we know that all three of the angles are the same in an equilateral triangle, and they all have to be 60 degrees because 180 divided by 3 is 60 degrees. So now what we are going to do is cut that triangle in half. So we end up with a 90-degree triangle. If you take a look at this bottom length, when we cut it in half, we are now left with 1. And if you take a look at this top angle, we split that angle in half, so we are left with now 30 degrees. And so let's just look at this one side of the triangle now, the right angle triangle. So the other side can just go. Just scratch that out. And that too as well. So we really just want to know this right angle triangle. We have 60 degrees, we have 30 degrees, 90 degrees. The hypotenuse is 2. The bottom length is 1. And we don't know the height of this triangle, so we are going to use Pythagorean theorem to find it. So this time we know C. C is the longest length, the hypotenuse. So C is 2, so 2 squared. A we'll say is 1, so 1 squared, and then B will represent as the height. So then we get 4 is equal to 1 plus B squared. Subtract 1 from both sides, so 3 is equal to B squared, and then take the square root. So that length is root 3. So we will write that on there. So let's just take a look at the lengths and compare them with the angles. The longest length is 2. That is across from the biggest angle. So 90 degrees across from that is length 2. The smallest length is 1, and that is across from the smallest angle, 30 degrees across from 1. Root 3 is about 1.7. You know it's going to be between 1 and 2 because the square root of 4 is 2 and the square root of 1 is 1. We're in between that. So that's going to be your middle length. So now we're going to take a look at both of these triangles and use them to find the exact values of sine, cos, and tan of 30 degrees, and then sine, cos, and tan of 60 degrees, and sine, cos, and tan of 45 degrees. So when asked to find these angles, you should always have the two triangles written down and refer to those. It's very hard to memorize all these ratios in your head. So we're going to look at sine of 30. So we're going to locate 30 degrees. It's in the second triangle. Sine is opposites over hypotenuse. So it's 1 over 2. And I'm not going to label the triangle because the reference angle is going to change. Opposite of 30 is going to be different than opposite of 60, although the hypotenuse always stays the same. Next, I want cos of 30 degrees. So again, here's my 30. Now I want the adjacent over hypotenuse. So that's root 3 over 2. And then I want tan of 30 degrees. So now I want the opposite over the adjacent. So that's 1 over root 3. And you can leave your answer as this. I'm happy with that answer. But the textbook might look different. Also, your calculator might look different if you are checking your answers with your calculator. What your calculator often does is it rationalizes the denominator, meaning it doesn't like that square roots in the denominator. So what it does is it multiplies the denominator and the numerator by root 3, and then the numerator becomes root 3 because 1 times root 3 is root 3, and the denominator is 3 because root 3 times root 3 is root 9, and the square root of 9 is simply 3. So again, I don't mind if you leave it as 1 over root 3, but just be aware that is equivalent to root 3 over 3. Okay, so then we're going to do the same thing for 60 degrees. So sine of 60. So again, we're locating 60. It's in the same triangle, but this time the opposite is root 3 and the hypotenuse is 2. So we're going to write that as root 3 over 2. And then cos of 60, the adjacent is 1 over 2. And then tan of 60 is the opposite, which is root 3 over the adjacent, which is 1. So root 3 over 1 is simply just root 3. And you may have noticed that sine of 30 is the same ratio as cos of 60, and cos of 30 is the same ratio of sine of 60. And we look more into that when we graph the sine and the cosine function in the next unit. Okay, and then we're going to do the same thing for 45 degrees. So 45 degrees is in the first triangle. It doesn't matter which one you use because the opposite and the adjacent for both are 1. So sine of 45, you're looking at the opposite, which is 1, over the hypotenuse, which is root 2. So 1 over root 2. And again, your calculator will probably rationalize that denominator. So you would multiply the numerator and the denominator by root 2. So you get root 2 over 2. Cos of 45 is the adjacent over the hypotenuse. So again, you get 1 over root 2, which would then just be root 2 over 2. And then tan of 45 is the opposite over adjacent, so 1 divided by 1, which is simply 1. So all of these ratios are exact, meaning they are left as a fraction if necessary. We don't put them into decimals, and we found them all without using a calculator. Not only are you expected to find the exact ratio for these 3 angles, you also need to know how to do it for all angles that have one of these 3 angles as a reference angle, and that's what we're going to talk about next. So before we look at a couple examples, let's go back to the unit circle. I have identified where 30, 45, and 60 degrees are on the unit circle. So that again means that that is the angle that goes from the positive x-axis in the counterclockwise direction. So this blue line is 30 degrees. This blue line over here in quadrant 2 also has a reference angle of 30 degrees, which is this angle between the terminal arm and the negative x-axis. So that means the actual angle is 180 degrees minus 30 degrees. So that is 150 degrees. And then in the next quadrant, 3, again, you have a reference angle of 30 degrees, but this time you're going 180 degrees plus 30 degrees. So this is 210 degrees. And then finally in the fourth quadrant, the reference angle is 30 degrees. Again, make sure your reference angle goes to the x-axis, not from the y-axis. So this is your reference angle in here. So that is 360 degrees, take away 30 degrees. So this angle is 330 degrees. So all of these blue angles all have a reference angle of 30 degrees. So they will all have the same exact ratios as 30 degrees, although some might be negative depending on if you're finding sine, cos, or tan and which quadrant they lie in. So again, going back to cast. So we will now do the same thing for 45 degrees, which is in red. So 45 degrees is here, and now that means that the angle from the positive x-axis is 45 degrees. So in quadrant 2, the reference angle is 45 degrees. So to get to that angle, we do 180 minus 45 degrees, which is 135 degrees. Then in quadrant 3, again, your reference angle is 45 degrees. So to get to that angle, we do 180 and then 45 degrees more, which is 225 degrees. And then in the fourth quadrant, your reference angle goes between the terminal arm and the x-axis. That's 45 degrees. And so that's 360 take away 45. So that angle is 315 degrees. So again, all four of those red angles are going to have the same ratios, but some will be positive or negative depending on the ratio and which quadrant it is in. And then finally, we will do this for 60 degrees. So 60 degrees is the reference angle on all of these green terminal arms. So in the first quadrant, it's 60 degrees. In the second quadrant, it's 180 minus 60. So that's 120 degrees. In the third quadrant, that is 180 plus 60. So that's 240 degrees. And then in the fourth quadrant, that is 360 minus 60 degrees. So that is 300 degrees. So you are expected to be able to find the ratios for any of these angles without using a calculator and using those special triangles as well as remembering cast. So let's do 4 examples together on how we bring the unit circle and the special triangles to find these exact ratios. Again, all without a calculator. So the first question is tan 240. So the first thing I'm going to do is identify the reference angle. So I'm going to make a unit circle and then I'm going to draw where 240 is. So 240 is between 180 degrees and 270 degrees. So it's in here. And then I want to identify that reference angle. So I've got 180 and then I need to go 60 more to get to 240 degrees. So that means the reference angle is 60 degrees. So I can write that tan of 240 is equal to tan of 60 degrees. But I'm not finished yet. I have to just make sure that it's going to have the same sign. So tan of 60 degrees is always positive because it's acute. Acute angles are always positive. Tan of 240 might be negative. It depends which quadrant it lies in. So we're finding tan of 240. 240 does lie in the T section, so actually tan of 240 is positive. So this statement is true. I'm just going to leave it like that. So then that means that tan of 240, all I need to do is find tan of 60. So I'm going to draw that special triangle that contains 60 degrees. So that's 60, 30, 90. Hypotenuse of 2, shortest length of 1, and the middle length of root 3. I want tan. Tan is the opposite over adjacent from the 60 degrees. Opposite of root 3, adjacent is 1. So I'm then going to just say that tan of 240 is root 3 over 1, or which is just root 3. So really what I'm looking for as a final answer is that tan of 240 is equal to root 3. These questions are basically right or wrong. So sine of 300 degrees, again, I'm going to draw the unit circle. I'm going to identify where that angle lies. So it's between 270 and 360. So the reference angle is 60 degrees again. Again, because this angle here is the 300. So I can write that sine of 300 is equal to sine of 60, but I just have to check the signs first. So I'm going to write cast. This 300 degrees lies in the section where the cosine is positive, only the cosine ratio. I'm trying to find the sine ratio. So that means this angle, sine of 300, it's going to be negative. So I'm going to take the sine of 60 degrees, which is positive, and I'm going to have to make that negative. So that sine of 300 is negative. And then I'm going to go back to my triangle, because 60 degrees, I'm going to use the same triangle here. 60 degrees, this time I want the opposite, root 3, over the hypotenuse. So I'm going to say, and I didn't leave myself a lot of room, that sine of 300 is equal to negative root 3 over 2. So again, I draw where my terminal arm for 300 degrees is. I find the related angle, which is 60. So then I say sine of 300 is equal to sine of 60. But then the big thing, the hardest part is knowing if it's positive or negative. Sine is negative in quadrant 4. So I'm going to put that, I'm going to take the sine ratio of 60, which is positive, and I have to make it negative. So I add in that negative. Sine of 60 is positive root 3 over 2, so sine of 300 is negative root 3 over 2. In part C and D, I'm actually asked to find the reciprocal ratio of angles. So in part C, I want cotangent of 150. So how I'm going to deal with this is first find the tan ratio of 150, because cotangents and tangent have reciprocal ratios, and I'm more comfortable finding the tan ratio. So I'm going to find tan of 150 first. So I'm going to draw where 150 is. That's in quadrant 2. So that's 150 degrees, and that leaves 30 degrees as my reference angle. So I'm going to say that tan of 150 is equal to tan of 30 degrees. And now I'm just going to see if it's going to be positive or negative. So I'll write cast. It is in the S quadrant. Quadrant 2, only the sine ratios are positive. So that means this tan of 150 is going to be negative. So I'm going to find tan of 30 degrees, which is going to be positive, and then I have to make it negative. So I'm going to go up to the same special triangle above here, and now I'm going to look at the reference angle of 30 degrees. I want tan, so that's opposite over adjacent. So that's 1 over root 3. So I am going to say that tan of 150 is equal to negative 1 over root 3. So the 1 over root 3 comes from the triangle. The negative is because it's in this quadrant 2 and only the sine ratio is positive. So again, you can check in your calculator. Tan of 150 should be a negative ratio. But we're actually not done this question because I did not ask what is tan of 150. I asked what is the cotangent of 150. Cotangent has the reciprocal ratio. So what we're going to do is say, therefore, cotangent of 150 is just the reciprocal of the ratio we have for tan of 150. So I'm just going to flip the 1 and root 3, but you do have to keep it negative. If the tan ratio for 150 is negative, then the cotangent ratio is also negative. So make sure that they both stay negative. And then you can simplify that if you'd like. So cotangent of 150 is just equal to negative root 3. What I often see is students trying to find tan of the reciprocal of the angle of tan of 1 over 150. And then they really confuse themselves because I don't know what to do with that at all. And I see all sorts of strange math. It is not the angle that you take the reciprocal of. You work with the angle, with the ratio that you know, and then you get to the ratio. And once you have the ratio, you take the reciprocal of the ratio. So when you see cotangent, just think of tangent right away, find the tangent, and you will get part marks for that, even if you forget to flip it in the end. But find that ratio, and then you take the reciprocal of the ratio, never of the angle. So in the last question, secant of 135. So that means we really want to find cos of 135. 135 degrees is in quadrant 2. It's between 90 and 180. So this here is 135 degrees. So that means 180 minus 135 is 45 degrees. So that means our reference angle is 45 degrees and we want to find cos of 45. So again, we need to think about what the sign is going to be. So CAST. We are looking for the cosine ratio, but in quadrant 2, only the sine ratio is positive. So that means that cos of 135 is going to be negative cos of 45. So we need to use the other special triangle, the 45-degree one. So we have 45, we want cos, so that is adjacent, so 1 over root 2. So that means that cos of 135 is going to be negative 1 over root 2. But again, we don't want cos, we want the secant. So now that we have the cos ratio, it's very easy to find the secant ratio. Secant of 135 is just negative root 2 over 1, and you can write that as just negative root 2. So that is how we use special triangles to find exact ratios.